Okay, it's time. Good morning, good afternoon, everyone. Welcome to Indo Ag Science Café. I'm Cherry Kubota. I'm a professor at the Ohio State University, hosting this series of outreach effort, mainly toward indoor vertical farms, but we are going to expand the target next year so that it's more inclusive. So this outreach program is funded by USDA NIFA, Specialty Crop Research Initiative, where a number of scientists working together from Michigan State University, Ohio State University, Purdue University, and University of Arizona. So we are doing this every month. So I think we have been doing probably 4 years at least. So that's really good. Just wanted to give a upcoming schedule. So today, Dr. Chris Currey is going to talk about culinary herb production under controlled environment. And July, as tradition, we're gonna take the whole month off, or not, but no cafe basically, and it's just a tradition. And then August, I'm still working on the schedule, but I'm hoping to invite someone from Japan who can talk about hydroponic spinach production. They have been doing years, probably as long as, gosh, 20 plus years successfully. So I like to reveal what's the secret of spinach hydroponic production. So it might need a translation, but I am going to help that part also. That's the plan for August. And then September, from someone from Europe, giving a talk about R&D effort for vertical farms. So that's, and then more schedules coming up. So stay tuned. I like to make this learning opportunity and then also update of the technologies and science going into controlled environment agriculture. So with that, I'd like to introduce Dr. Chris Currey, who is from Iowa State University, talking about culinary herbs, growing culinary herbs under controlled environment. So I'm gonna stop sharing. And then by the way, recording is only for the presentation, up to the presentation. If you're new to this cafe, then we stop recording so you can ask questions during that time. All right, so I'm gonna stop sharing and then have Chris start sharing your screen.
Thank you so much for having me, Dr. Kubota and the Science Cafe crew. It's a real pleasure to be here. I hope that you are all enjoying your summer so far. This is one of my favorite times of year because the greenhouse is not quite as busy as it is, say, in January, February, March. So it's a kind of a nice change of pace for me. But today I'm going to talk about something I've been working on for quite a long time, or I guess not quite a long time. I guess I can say 10 years now. It will be 10 years on July 1st that I've been working on culinary herbs in controlled environments. And that pretty much started when I began my position here at Iowa State University. So really, I guess the question is, why culinary herbs? Well, why not? There are a couple of different reasons why I think herbs are a good crop. Well, one, they're a low barrier crop to get into controlled environment agriculture. And this would be similar for hydroponic leafy greens and lettuce. Maybe not spinach, which we need the master class in, but these leafy crops can often be a low barrier of entry, especially when compared to high wire vine fruiting crops like cucumber, tomato, and pepper. Makes it easier to retrofit facilities or accommodate new producers. It has short-term production cycles. So if you do run into a bit of a problem, it's not going to be that long to get back up and growing again. The other thing is that it can serve as a gap crop for ornamental producers. Now, we all know that bedding plants sold in the spring are the #1 greenhouse crop, but is this something else that growers could be growing in the off season? Maybe a holiday alternative to poinsettias. Again, like we already mentioned, it's easy to retrofit facilities for some leafy crops. It's also increasing in popularity amongst consumers. So this isn't just something coming from the production end, but people are more interested in culinary herbs. I think our food intelligence or our food IQ has been rising. I think that kind of started back with the organic and local food movements, and people just like better food, and culinary herbs are often a part of that. They're so popular, they're actually the 3rd most valuable crop grown in protected cultures. So those numbers are speaking. But what is the challenge with herbs? And I think this picture sort of summarizes the challenge with herbs, is that unlike a tomato greenhouse or a cucumber greenhouse or maybe a lettuce greenhouse, if you are an herb producer, you are going to have a large number of species. You're going to have a polyculture. And this is different than a lot of our controlled environment food crops. We're thinking more monocultures or maybe some different varieties of a species. But when we're looking at herbs, we have a lot of variety. Now, again, your primary herb is going to be basil. Behind that, it's going to be mint, but you have to still grow other things because you've got to have a complete program. And so that polyculture is really what makes growing herbs a challenge. And it's very similar to what makes growing spring ornamental crops a challenge for bedding plant growers. We have hundreds of different types. We're not just growing one crop of poinsettias or a crop of Easter lilies. We're not growing primary crops. We're growing a range of minor crops. Now, that can be a challenge, but for someone like me, a former greenhouse grower and someone who loves to do controlled environment plant research, this is an opportunity to try and provide science-based solutions for producers. And when we look at culinary herb production, there hasn't been a whole lot of research, especially relative to other popular controlled environment crops like tomatoes or lettuce. And there are a number of things that we're going to be concerned about that I've sort of listed up here, all the way from cultivars down through marketing. In today's talk, I'm going to look at primarily cultivars, production systems, nutrient solution, temperature, as well as light, both intensity and quality. So with that, let's get into some of the things that we have found about. So when we're looking to grow herbs, what do you want to try and select for growing? Now, for some species, there's going to be dozens of cultivars, like basil. Now, for others, there are only going to be just a few. Now, one thing that is sort of different from herbs compared to some other popular CEA crops is that there has been little to no breeding for controlled environment production, meaning developing cultivars for these controlled environments. Now, this is changing. We're starting to see some controlled environment bred basil, but will that go throughout the other herb classes? We're not sure. Until we have more genetics that are available to us, we're finding ourselves in a place where we need to utilize those existing genetics that have been bred for outdoor production and see what works well for the greenhouse. So we started with basil. Again, basil is going to be the most popular culinary herb, so we wanted to start looking at the varieties. So we got 35 different cultivars, and that included basil from the most popular class, which is going to be that sweet basil, but then we also had some purple or opal types, large leaf, cinnamon, Thai, bush, lemon, and holy basils. And if we look at a couple of different types of basil up here, you can see that we've got a wide variety across the different types. When we look at fresh mass, leaf index, or branches. And that would make sense that we'd see variation across different basil types because these different types of basil are fairly different. So of course, our purple basil is going to have less fresh mass produced than those green leaf varieties. We generally get lower photosynthesis when we have those purple leaf cultivars on a per leaf area basis. But let's dig down a little bit more into just one class, one type, and that's going to be sweet basil. Now, when we look at sweet basil, I have amassed sort of a smattering of cultivars here, just around a dozen or so, and we can look at the variation in just sweet basil cultivars alone. Again, we've got fresh mass, height, leaf index, and branches. What's going to be the most important for producers? Well, that's going to be fresh mass. So let's ignore some of that other data and just look at fresh mass. Just looking across the different types of basil, green, sweet basil cultivars alone, we've got a range of almost 3.5 to fold increase in our weight. When you look at Emily, we've got about 15 grams per shoot. When you look at Italian largeleaf, we've got just over 50 grams per shoot. Again, these had the same propagation time, approximately 3 weeks prior to planting, and they had the same production time in the greenhouse, but we got over 3 times as much fresh mass just by using that Italian largeleaf cultivar over that Emily cultivar. So this was just a very, very brief snippet, but I'd like to understate the importance of cultivar selection. It's going to be one of the simplest way to improve your yields. Now, for some customers, they may demand lower yielding cultivar. That might be, say, in the instance of basil, we might be looking at one of the specialty varieties, say that purple basil that produces less fresh mass. Now, we're not going to be able to substitute a high yielding green basil, green sweet basil, for that lower yielding purple variety. But when we do have multiple varieties available, do your own trials or try to talk with other growers and find those high yielding varieties. Because again, just selecting the right cultivar can increase your yield fairly sizably, depending on the cultivar you're currently growing. So once we figured out what we're going to grow, what are we going to grow it in? Now, there are a number of different production systems that we can use. In hydroponics, I'd like to refer to it as sort of a spectrum, right? And there are all sorts of different hybrid types of systems. But there are two systems that are very well suited for leafy crop production, for those leafy crops like culinary herbs. One is going to be NFT systems, and two, that raft or deep flow culture. Some people also call raceway culture. So here we have an example of a greenhouse that's been retrofitted with some channels for NFT production. So again, we've got those sort of gutters with the holes drilled in them. We've got that water coming through. Alternatively, here we have a deep flow system, or that raft or raceway system, where we have those polystyrene rafts on top of our nutrient solution. One of the benefits of these systems is you can often centralize labor, planting on one end and harvesting at the other. So what system should we use to grow culinary herbs? We wanted to again do a trial for that. Now, unfortunately, we couldn't get these at commercial scale to do trials with, but we replicated them in our greenhouses. And again, we used both a deep flow type system and an NFT system. Now, the deep flow system, you can see that it is raised up to the height of the NFT system. That was done purposefully. If we would have left them on the floor, we could have had different light intensities at plant height. Similarly, since we have in-floor heat in our greenhouse, we didn't want that to raise the temperature of our DFT systems. So with both of these systems, we got them at the same level. We have comparable supplemental light. We also used water heaters and chillers to make sure that we kept comparable nutrient solution temperatures across our system. And like you'd expect with any other hydroponic system, we maintained the pH and EC at target levels. When we look at the effect of cultivars, different cultivars grown in these different systems, look at the overwhelming effect of cultivar, which would we expect? Different plants have different responses. But look at the lack of effect of different production system, as well as the interaction of different cultivars and production systems. So this is sort of boring, but what this is showing is, again, systematic research demonstrating there is no real benefit to one system or another when it comes to productivity. So again, this research indicates these two systems are both useful for growing herbs. Now, sometimes people will say that one system may have a benefit for plant growth over another. For example, our DFT system, if they're on the ground, would have likely had a warmer temperature just from that in-floor radiant heat. But we tried to correct for all of those variables in how we set up our experiment. So we were just looking at the system itself. So again, we got comparable growth in both systems. So you don't need to select them based on anything inherent in the system that would affect the biological growth of our plants. Select them for the operational factors, such as the ease of maintenance. Maybe you don't want to be scrubbing raft, or maybe you don't want to be cleaning channels. You also want to consider ergonomics. If you're doing a cut and come again herb program where you harvest the shoots and come back and harvest again, you may want something that's going to be raised up like those NFTs. Alternatively, if you're just harvesting live plants, those rafts may be a good option because they can simplify your harvest. So again, think about operational considerations. We don't need to be concerned about how the system may affect plant growth. So moving on, let's look at nutrient solution electrical conductivity. So we often think of nutrient solution as sort of the lifeblood of any hydroponic system. We maintain those target nutrient levels by using the electrical conductivity of our nutrient solution. That total EC reflects the overall status of our nutrient concentration. And we use that again as our benchmark in recirculating water culture to try and make sure that we're providing adequate nutrition to our plants. So we wanted to again look at the response of culinary herbs to nutrient solution electrical conductivity under different systems. But we wanted to do it with a twist and look at it under different conditions. Often we hear about growers having a summer nutrient solution and a winter nutrient solution. So we want to look at these different nutrient solutions under two different daily light integrals. One we call a low daily light integral, and that's going to be somewhere maybe in January in Iowa. And the other would be at a higher daily light integral, maybe around 16 moles per day. That'd be something like April or May. And this represents sort of when you may want to use supplemental lighting in the winter, or when you may have low light, and when you have adequate lighting in the greenhouse, or you'd be using supplemental lighting. We used 4 different species: basil, dill, parsley, and cilantro. And for our basil, we used a few different cultivars. And then again, we had 5 different electrical conductivities ranging from 0.5 decisiemens per meter or millisiemens per centimeter up to 4.0. So here is the picture of our sweet basil. This is the cultivar Nufar, grown under a low DLI, that top row, or a high DLI, that bottom row, under a range of different nutrient solution ECs, again, 0.5 to 4.0. Now, while it might look like there's a slight promotion of growth under the low DLI as the EC increases, for both the low DLI and the high DLI, we found no effect of electrical conductivity on the fresh mass of our plant. So it might look like that, but when we look at the data, there was no effect on fresh mass. We did see a difference in fresh mass across electrical conductivities when we had basil growing under that high DLI as compared to the low DLI, but that was an effect of light. We did not see an effect of electrical conductivity on the fresh mass or the fresh weight of our crops. What we did see, though, was an effect of electrical conductivity, that EC, on our tissue nutrient concentrations. And here we see the nitrogen concentration in our sweet basil foliage. And as I mentioned, you can see it increasing as EC increases. But what is the target nitrogen concentration we're trying to get in our leaf? Well, we're trying to get 4 to 6%. You can see that we're well within that sufficiency range across the entire range of electrical conductivities, most notably at those very low electrical conductivities, where you saw anywhere from around 4.7 in the high DLI, those open circles, or just under 5.2 in those closed black circles for that basil grown under the low DLI. So again, even under that very low EC, we had more than sufficient nitrogen in our leaves. And the results, again, very similar. Here I've got high DLI cilantro and low DLI cilantro, as well as high DLI dill and low DLI dill, grown across this range of nutrient solution ECs. And again, it's the same story. We didn't see an effect of EC on the fresh mass or the fresh weight, the yield of our crops, but we just did see that effect of light. Again, not a surprise when we think about light. And I'll come back to that later in the presentation when we talk about photosynthetic light and herbs. But it was surprising to see pretty much a lack of EC response. Increasing our fertilizer did not increase our yield for our herb species. So that was pretty interesting. Again, herbs, they're sort of a nutrient use efficient species. Think of where they're from, oftentimes a poor environment. A lot of herbs will come from that Mediterranean region where you have maybe poor nutrient levels in the soil. And we're seeing some of that play out in our production. So that EC, again, had no negative impact on tissue concentrations either. So not just the fresh mass or that fresh weight, that yield we're thinking about, but the low ECs didn't result in plants that were more chlorotic, maintaining them at a very, very marketable place. In fact, we still had luxury consumption for some crops. So EC management, again, is not going to be real critical for culinary herbs. Now, one thing you do want to keep in mind is you want to look at individual nutrient concentration over time. So as these recirculating systems are replenished with stock concentrated solutions, you might be maintaining the same EC, but you'll start to get those imbalances in nutrient concentrations in your nutrient solution, because not all nutrients are taken up in the same proportion that they're being added into our nutrient solution. So you do still want to be mindful of your nutrient solution and watch for nutrient imbalances that may occur over time, even when you're maintaining that target EC that you have. So I would love to follow this up and talk about pH work, but we can sort of kick that ball back to Dr. Kubota. We know that she's done some work with low pH with spinach and basil. So she can speak to basil and pH. One exciting thing is right now, I do have a student who is getting ready to start graduate school this fall, and they're going to be working for the next 2 years on pH levels for nutrient solution for culinary herbs grown hydroponically in controlled environments. So I will be back with the other half of this sort of nutrient solution story when we think of electrical conductivity and pH, but it's just going to take a couple of years to get there. So stay tuned. Okay, when we're thinking about our controlled environment, one of the biggest advantages that we have is that we get to create those conditions conducive to growing. And often we think about that winter where we've got that warm greenhouse compared to the cold outside. Well, it's not just that we've got a temperature that is conducive to growing plants. We can carefully control that temperature in controlled environments. And temperature is going to be the primary determinant or influencer in the rate of plant development. We can use these air temperatures not only to determine our growing conditions, but also to control crop development and predict yields. Maybe we're trying to enhance development and speed up growth. So we're going to raise the air temperature, or maybe we need to slow something down. We can use models to try and develop or predict what's going to happen in response to temperature changes. However, again, going back to the polyculture of herbs, we have a number of different species that are likely going to have different temperature responses. So when we look at the plant responses to temperature, this is what it normally looks like. Plant growth is going to increase up to a maximum rate of development, and then it's going to decrease. That optimum temperature is going to be right here. That's where our growth is maximum. Our maximum temperature is when plant growth stops due to heat stress. That base temperature is the temperature at and below which plant development stops due to those cold temperatures. And between our base and optimal temperatures, we call this the linear range because it is fairly linear between those two temperatures. Thankfully, we're also normally working within this linear range when we're talking about the plant responses to temperature in those temperatures that we're normally using in controlled environments. But how do we get these data? How do we determine the base temperature, the optimum temperature, and the max temperature and calculate that linear range? Well, we've got to do some modeling. So over a number of years, this was something that a number of students worked on with me. We had 5 different air temperatures ranging from 11 Celsius to 35 Celsius. And over 2 years, we ran 16 different species in cultivars. Basil, 4 different species, cilantro, 2 different cultivars, and then a host of different herb cultivars. And so again, we put them through these temperature treatments to try and model their responses. And this is just a good example of a typical response. So here we have lemon basil. It is a cold sensitive plant. As you can see here, it's going to have a low base temperature, fairly warmth tolerant. That optimal temperature is somewhere in the low upper 20s or lower 30s. So again, low base temperature, high optimal temperature. Now let's contrast that to dill and parsley. You can see much more cold tolerant crops. Look at the growth at the 11 degrees Celsius, and their calculated base temperature was several degrees lower than the basil. But you can also see those those optimal temperatures are going to be somewhere closer to 23 degrees as opposed to the upper 20s and 30s that we saw for basil. Now, I don't have the time to go through all of those 16 different species and cultivars, show their different responses, but I would like to just demonstrate how we can use these responses. So here we have the response of dill to our growing temperatures. So again, you can see development increases as temperature increases, then it starts to decrease as it gets too warm. We were able to calculate that optimal temperature as 22.9 degrees, like I said, right around 23. And so we can take out those temperatures that are above that optimal temperature, and we can calculate that base temperature right around 8 degrees Celsius, and then we can create that linear range between our base and our maximum temperatures. And this linear range is going to actually be really useful for helping us schedule plants. And now I keep on saying this, but let me show how we can use this data to try and make good decisions. So we'll go back to the most popular plant, the most popular species, and we've got basil. And so what are we going to do? Let's try and predict our basil harvest. So we usually plant a very small basil seedling right around 1 gram of fresh mass when it goes into our system. Our target is going to be that 3/4 of an ounce or 21.3 grams. It's great if one shoot or one hole can equal that clamshell that we're trying to sell. Just like lemon basil, sweet basil is another cold sensitive species with a warm optimal temperature. So we take that response of basil to temperature, we kick out those temperatures above that optimal temperature. We've got our linear model, and that's going to be the amount of fresh mass gain per day for a given temperature. And using that model, we can look at growing at 18, 20, or 22 degrees Celsius. And we get these fresh mass rates, again, grams per day. And we can see that at 22 degrees Celsius, we'll actually have a harvestable shoot at 22 days. If we grow a little bit cooler at 20 degrees, drop it down 2 degrees, we increased our harvest by 5 days, getting there at 27 days. Alternatively, if we drop it down to 18 degrees Celsius, it will take 5 weeks to get to that harvestable shoot using our predictive models. So that's one of the big benefits, is that in a controlled environment, we can control our growing variables, and air temperature is going to be one of these variables that we're definitely going to be able to control. These predictive models are going to be useful for trying to determine how we're going to have change whenever we're modifying our air temperature in a controlled environment. Again, when we have a polyculture, any decision we make is going to affect all of our species differently. And having these different responses categorized are going to be useful, because one thing you may have is the luxury of being able to group temperatures or group crops by temperature responses. If you have maybe 1, 2, or maybe even a third different air environment, since some greenhouses, they are separate greenhouse bays, you may have separate rooms in an indoor production facility. You could potentially group your species by their temperature responses. So you could be growing them all at their optimal conditions. Maybe you could have a cooler environment for things like cilantro, parsley, dill, and you can have a warmer environment for those heat-loving species like basil. So now, in addition to the air temperature that's going to be controlling the rate of plant development, we also want to look at our light. Light has a very large influence on the growth of plants, and we sell mass. So it's a little bit different than ornamental producers when they sell a potted geranium or a bouquet of flowers. They're selling units of plant, a dozen stems or a single pot. But when we're growing controlled environment food crops, we are selling by unit weight. Now, we might be selling a head of lettuce, but that head is only harvestable once it reaches a target weight, like say 300 grams or something like that. As a result, we really want to manage our photosynthetic light, because again, that photosynthetic light can have a large impact on the growth. Now, for some species, we might need to be more concerned about day length or photoperiod. But for the most part in culinary herbs, we're generally growing in a short enough crop cycle, 3, 4, 5 weeks. We're usually not have to be too concerned about the day length or the photoperiod that we're growing our crops under. So again, we can have large ranging growth. So we wanted to model herb growth in response to daily light integrals. Again, we wanted to do this across a range of DLIs, because in greenhouses where you have varying solar light, we want to know how plants respond across a range of DLIs. We chose 8 different species for this work, basil to thyme. I really wish that we had an herb that started with A and an herb that started with Z, so we could have herbs from A to Z, but I guess we went from B to T. So what did we see? Well, again, you can probably predict the response. Yield increased with DLI. For the majority of herbs that we grew, we saw a linear increase in response to DLI. Now, I should note that we only got up to around 20 moles of light in the greenhouse. Going above 20 moles of light in the greenhouse gets fairly challenging in our greenhouses, because we have fog cooling, And in the humid conditions of summer, when we're normally trying to achieve those high DLIs, we just get too much fog in the greenhouse. So we're limited up to about 20 moles. Now you do see here that parsley, mint, and sage started to taper off a little bit on the upper end of these DLI ranges, as opposed to basil, cilantro, dill, thyme, and oregano that kept on increasing. Well, as a result, we can classify these herb responses to light. Now, based on that diminished growth at the upper end of the range that we evaluated, we classify mint, parsley, and sage as moderate light plants. Now, these categories are with respect to food crop light requirements. We're not comparing them to ornamental plants. So we classify mint, parsley, and sage as moderate light crops, whereas those remaining species, basil, cilantro, dill, oregano, and thyme, we classify as either high or very high light crops. Again, we can't differentiate between those two requirements because we only got up to that 20 mole requirement. We didn't get to go above that range. So which herb crops are you going to light? Or which herb crops are you going to grow under a greater amount of light? As you can see, or as we saw in the previous slide, they all benefit from an increased amount of light, but not all plants will benefit equally. So this is something that I think I can just say I stole from Dr. Kubota. Imitation is the sincerest form of flattery, whether it's music or science. And I calculated the par productivity of culinary herbs. And what the par productivity is that is a measurement of that harvestable yield portion of a crop relative to the light input. And this helps us make decisions between different species or between different cultivar or between different crops, looking at the benefit that we'll get back for that light that we're adding to. Now, based on our research, dill is going to have the highest par productivity. And right behind that, you can see we've got basil. So it's a good thing that basil ranked high on par productivity. That's going to most likely be the herb that is occupying the greatest amount of area in your production units. So that is going to be a good one to light. Now, if you are growing oregano, you can see that came in very, very low on the par productivity list. I'd go put your light on a different crop, something that's going to give you more yield in response to those additional photons that you're providing. So again, herbs have a moderate to high light requirement. That par productivity, though, as you can see, vary widely. So make sure that we're determining the best crops to light. And I'm going to use that as a segue into a discussion on supplemental light. A lot of times, that's going to be the only way that we can appreciably increase light levels inside of a greenhouse is by using supplemental light. We can try and maximize the transmission of ambient light into our greenhouse by keeping clean glazing material, minimizing overhead structure, superstructure that may be shading it. But the only way to increase it above that amount that's transmitted is to use supplemental light. Now, high pressure sodium lights are still fairly widespread and standard in the greenhouse industry. But LEDs, light emitting diodes, are an increasingly popular alternative light source. Now, there's a number of benefits to LEDs that we've probably all heard about, right? There's the potential for lower energy use. There's also the possibility to use that narrow spectrum lighting. And we can use that narrow spectrum lighting for a number of different things. Some of us have heard of using blue light or increasing our proportion of blue light to try and keep plants more compact. It's especially of interest for those ornamental plant producers who are growing things in containers. But we were also interested if we could use that spectrum to modulate not just the growth, but potentially the flavor of our herb crops. Those polyphenolic compounds, those secondary metabolites that we find in herb crops are often the result of a stress response because that's a defense mechanism to try and reduce herbivory. The culinary herbs will upregulate the production of these compounds in response to stress. And while other things may not like them, those compounds are exactly why we're growing our herbs, because we like the flavor of those compounds. So can we grow a better herb using different light? So we take a look at herbs grown with 100 micromoles of supplemental light provided by either high pressure sodium lamps, LEDs with a low proportion of blue, about 7%, and the rest of the balance, 93% in red, or LEDs with a high proportion of blue, 30%, and the rest in red. And we looked at 3 different herb species, basil, dill, and flatleaf parsley. Now, when we look at the plants when they're done being grown, you can see that we have an effect on plant height, right? You can see that those plants are a little bit more compact under those that high blue light source. We did get slightly less fresh and dry mass, but it was not statistically less with those LED grown plants versus those HPS grown plants. But we're not trying to grow compact shoots. That's not of concern here. Again, we're trying to grow shoots that have good flavor. You can see that as we went from high pressure sodium lamp to the low blue LED to the high blue LED, we started to get an increase in some of these polyphenolics in basil. We saw a similar response with dill and a similar response with parsley too. So we did see some of this enhanced polyphenolic production or this enhanced supplemental secondary metabolite production by using supplemental light sources that had a higher concentration of blue light. Well, let's take that a little bit farther. In our first study, we only went from 0 to 30% blue light, and we wanted to go above that 30% threshold. In this study, instead, we went into growth chambers. So these were entirely sole source LED lighting. We didn't have any ambient lighting. And we went from 0% blue and 100% red. And then we started to swap out red for blue photons in 20% increments. So again, 0% blue, 100% red, 20% blue, 40% blue, 60% blue, 100% or 80% blue, 100% blue, and as well as a white light comparison. So what did we see? Well, here is a picture of our plants. And you can see as we go from left to right, we can see that dose response of that basil getting shorter as the proportion of blue light increases. And this makes sense based on what we have already discussed, ornamental growers using blue light to grow more compact plants. But what's really interesting is that at 100%, all of a sudden, you get the tallest plant of the pile. We will come back to that anomaly, and I will hopefully explain what happened. And then finally, we've got our white light over here. So that was the plant growth, but what about those flavonoids, those secondary metabolites? Well, as we suspected, we had an increase of all those compounds with increasing blue light proportion. So again, we saw those increases. Those treatments that were statistically different than the white light control have asterisks by them. So again, we can use blue light to enhance these secondary metabolites and potentially have a more flavorful basil, but it may come with a penalty. So like I mentioned earlier, the basil grown under the 100% blue light were the tallest plants. And it wasn't because they had any more pairs of leaves. The node number on all these plants were the same across all of our treatment. They were all grown at the same air temperature. And as we already discussed, air temperature controls the rate of development. We're going to have the same leaf number. What it was is it was a difference in internode length. We saw that elongation occurring because of the 100% blue light. And this anomaly where you have under 100% blue light with no red light, you have this excessive elongation. And I remember where I first saw this, it was Dr. Kubota's graduate student or former graduate student, Ricardo Hernandez. He had the exact same response in research that they were doing on sole solar lighting of cucumber seedlings. 100% blue light for those cucumber seedlings made them shoot up and they actually elongated. So very similar response. It has to do with that phytochrome photo equilibrium that you get under 100% blue light without any red light in there. So like I mentioned, we want more flavorful basil, but what's that going to do to our yield? We actually started to see a penalty we started to see a yield penalty. Our leaf dry mass and our root dry mass was actually going down with our increasing blue light. We were getting that smaller leaf area under that greater proportion of blue light. So it was getting more flavorful, but we were getting less mass and smaller leaves. And we don't want more stems. What I've got over here on the side is we've normalized the leaf, stem, and root dry masses to that total plant dry mass. And what happens is under the increasing proportion of blue light, not only do we get less leaves, but we got more stems. And you can see that proportion of stems as a proportion of the total mass increasing as you get that increasing blue light. So for supplementing ambient light, again, you can use HPS and LEDs. You can get comparable growth, so that's great. LEDs can substitute in. In fact, LEDs may be able to provide a little bit of a benefit by increasing the proportion of blue light that you're going to be providing to your plants. But you can take this too far. We want to balance flavor and yield. We don't want to have super high polyphenolics, but have very small leaves and less fresh mass as a result of it. So 38 minutes later, where are we? Some conclusions for CEA herb production. Select high yielding cultivars. It seems like a well duh, but you'd be surprised at the opportunities that people are leaving on the table by not seeing what other cultivars might produce more fresh mass. I'll just throw this in an aside, another really easy one. A lot of times we're growing herbs in NFT channels that have those holes that are pre-drilled on 8-inch centers. That's for butterhead lettuce. There's a local grower around here that was using those channels with holes on 8-inch centers. I told him to go in his systems and drill a hole in between each of the other ones, so he had them every 4 inches. He drilled those holes and was instantly able to double his yield. He had to use extra substrate and extra seed too, but just growing on that higher production density. Sorry for the aside. Select a system that is going to be cost beneficial for you or is going to be ergonomic for your employees. Think of those operational considerations. Don't get hung up on any advantage a system may have outside of those operational characteristics. We can correct EC, we can correct nutrient solution temperature, but we can't correct the height when we're bending over to harvest. Manage your nutrient solution EC to minimize nutrient imbalances over the long term. So manage your EC for growth, but also make sure that you're looking at those concentrations so we don't have imbalances developing over time. You might be able to run a little bit higher EC that might extend the period of time of those imbalances from occurring. Your temperature and your DLI models can help you predict what changes are going to happen as you alter your growing temperature or as you're deciding what light intensity to grow. And also, don't forget about what added value you can potentially provide with blue light and the narrow spectrum LED lighting that can provide that for your blue light. So with that, here is just a selection of partners that helped. These are also some of the graduate students who have helped along the way. I'm so thankful for the awesome time. And with that, I would like to take any questions that you've got.
Well, thank you so much, Chris. It was excellent. It was so comprehensive. I really enjoy always your talk. So thank you so much.